At first, no one believed it. The signal came in quietly, a thin spike of data, buried in the routine logs from the Neil Gehrels Swift Observatory, dated October 3rd, 2025. Nothing unusual, at least not until someone noticed the signature hiding within. The unmistakable spectral trace of hydroxyl radicals, fragments that can only appear when water molecules are broken apart by sunlight. But that was impossible. The source of the signal, the interstellar object known as 3I Atlas, was still 4 astronomical units from the Sun, far beyond the frost line, where ice should sleep untouched for centuries. Yet the readings were clear, repeating, and spreading across instruments worldwide like a whisper of disbelief. Within hours, cross-checks began. From the ESA's ExoMars Trace Gas Orbiter, orbiting Mars, came fresh images dated October 7th, a glowing, overexposed coma surrounding a dark nucleus, yet no visible tail. Something was happening out there, something that didn't fit the known playbook of comets or asteroids. Radio telescopes in Hawaii, infrared eyes in Chile, and amateur astronomers in Japan all reported the same anomaly, a brightening pulse, as if the object were breathing, waking, or shedding something unseen. And so, a quiet night at NASA's Swift Operations Center turned into the beginning of a global alert, a moment when even the most skeptical scientists looked at the data, then at one another, and realized they were watching an event that by all logic should not exist. Tonight, we embark on a new journey where the theme of something impossible just occurred. Around 3I Atlas appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe. But only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. From there, the story unfolds, a hyperbolic orbit confirmed between September 29th and October 3rd by the Minor Planet Center, an interstellar trajectory impossible to dispute, and a series of haunting observations from Mars, revealing a coma without a tail, a light that refused to fade. Yet the heart of the mystery remains the same. How could something so far from the Sun begin to release water, as if touched by a heat no one could explain? The universe presents us with a phenomenon that defies our established textbooks on cometary behavior. We have named it an impossibility. The central enigma is this: water had awakened far too early. In the ultraviolet spectrum of the interstellar comet 3I Atlas, the distinct signature of the hydroxyl molecule was detected, a telltale byproduct of water ice being broken apart by sunlight. According to current models, this level of activity should only commence when a comet ventures much closer to the warmth of a star, its frozen volatiles slumbering in the deep cold of interstellar space. The conventional explanation suggests that localized pockets of more volatile ices, such as carbon monoxide or carbon dioxide, could have been the first to sublimate. Their energetic release might have excavated fresh water ice, dragging it into the vacuum in a premature outburst. This is a plausible, almost elegant solution. Yet, it fails to account for the sustained and significant nature of the outgassing observed by the Swift Observatory's ultraviolet and optical telescope in the final months of July and August 2025, a finding that would not be publicly revealed until the beginning of October 2025. The data was unequivocal. The water was active at a distance where it should have remained inert. This leads us to a more profound and unsettling hypothesis. Could 3I Atlas possess an internal furnace? Imagine not just random pockets of gas, but a structured, trapped reservoir of carbon monoxide and carbon dioxide, acting like a thermal battery, storing cold interstellar energy, only to release it as a controlled heat source upon a predetermined trigger. Or perhaps we must consider a far more radical proposition. What if this object is not a natural vagabond at all, but a crafted vessel? A glass bottle cast into the stellar ocean by a distant intelligence, equipped with an active heating mechanism designed to broadcast its chemical signature precisely when it enters a new planetary system. The anomalous richness in carbon dioxide, as later described by NASA, would then be not a quirk of chemistry, but a feature of its design, a chosen propellant for its message. Is the early awakening of water not a puzzle of physics, but the first line of a letter we are only just learning to read? The evidence supporting this early activity is not isolated. The initial data from SWIFT found a powerful corroboration in the early days of October 2025, when the European Space Agency's ExoMars Trace Gas Orbiter, stationed at the Red Planet, also captured 3I Atlas in its instruments. Its observations confirmed that the object was already dynamically alive as it passed near Mars, reinforcing the notion that its internal processes had been underway for a considerable time. This convergence of data from two independent missions, one near Earth and one at Mars, transforms a single anomaly into a consistent pattern of behavior. We must then analyze this through escalating layers of complexity. The first level is a local abnormality, the simple premature release of gases. The second level proposes a novel physical structure, perhaps a porous, multi-layered foam-like architecture that allows sunlight to penetrate deep into the nucleus, creating internal hotspots that defy standard thermal models. But the third level of analysis compels us to look beyond known geology. What if the mechanism is artificial? A surface coated with an engineered black metasurface, a material designed to possess perfect absorption across a wide spectrum of light. Such a material would not merely reflect or absorb sunlight naturally, it would be engineered to capture nearly every photon, converting light into heat with maximal efficiency to intentionally trigger early and controlled evaporation. The implications of this are staggering. If water ice can be coaxed from its slumber at such vast stellar distances, then the entire paradigm of prebiotic material transport between stars must be rewritten. The journey of the building blocks of life becomes far more efficient, no longer constrained by the strict thermal limits we once believed were universal. If this is a natural capability of some interstellar objects, then the galaxy may be teeming with such chemical messengers. But if it is by design, then what other messages have we missed, and how many more such bottles are currently sailing the void, waiting for a recipient? The answer may lie in the intimate portrait being captured from Martian orbit. From the stark, red plains of Mars, a new eye opens upon the cosmos. The ExoMars Trace Gas Orbiter, a silent sentinel, turns its sophisticated instruments away from the planet it studies and towards the deep black. Its target, the interstellar visitor, known as 3I Atlas. In the first week of October 2025, as the object made its closest approach to the red planet at a distance of 0.19 astronomical units, the TGO's Cassis camera captured a sequence of images that would confound expectations. The data revealed a bright, shimmering coma, a halo of gas and dust illuminated by the distant Sunday. But where conventional cometary science predicted a long, sweeping dust tail, there was near nothingness. The tail had all but vanished, leaving behind a ghostly, asymmetric envelope. This was humanity's first close-range look at an interstellar object from the orbit of another world, a moment that redefined our perspective. How could an object with such a vibrant coma lack the defining feature of its kind? The initial, most conservative explanation lies in the geometry of observation. Scientists suggest this could be due to the phase angle, the specific alignment between the Sun, the comet, and the observing spacecraft. According to current models, the dust particles composing a comet's tail are most visible when they scatter sunlight directly towards the observer. From the TGO's unique vantage point in Martian orbit, the geometry may have been such that the dust trail was rendered virtually invisible, a faint smudge against the backdrop of space, while the coma, a sphere of material, remained prominently lit. The Mars Express orbiter, collaborating in this unprecedented campaign, provided supplementary data that seemed to support this simple optical illusion. Yet, if the geometry was so unfavorable, why did the coma itself appear so brilliantly and complexly structured, hinting at a level of activity that should, by all rights, have produced a visible dust tail regardless of the viewing angle? This leads to a second, more intricate hypothesis centered on the object's fundamental composition. The dominant scientific interpretation posits a regime of gas-driven outgassing. In this scenario, 3I Atlas is not a dusty snowball but a volatile rich body where the ices sublimating from its core are predominantly gases like carbon monoxide and carbon dioxide. These jets of gas erupt with such force that they carry away relatively few solid dust particles. The result is a brilliant coma of excited gas molecules and a faint, narrow ion tail swept back by the solar wind, while the more reflective dust remains trapped close to the nucleus or is ejected too slowly to form a prominent trail. The data from the TGO's spectrometers would indeed show strong emission lines for these exotic ices, but that does not account for the peculiar plasma signatures and the abrupt, sharp boundary of the coma, which resembles not a gentle dissipation but a deliberate termination. What if the explanation is not a lack of dust, but an active suppression of its visibility? A more speculative hypothesis emerges. Perhaps 3I Atlas is enveloped in an invisible cloak, not of fiction, but of plasma. Intense and anomalous magnetic fields, generated by the object's unknown mineralogy, or even its internal structure, could create a localized magnetosphere. This dense, shimmering sheath of charged particles would act as a screen, scattering and absorbing the light from any dust particles that do manage to escape, effectively blurring the tail from our view. The coma we see is then not just a cloud of gas, but the luminous boundary of this protective bubble. Is it possible we are witnessing not a natural comet, but an object whose very nature includes the ability to manipulate its immediate environment? This line of inquiry compels us to consider an even more profound possibility, one that reaches back into the deep time of the galaxy. The faint, almost severed appearance of what little tail remains suggests another force at play. We must contemplate the existence of an ancient, relic interstellar magnetic field, still clinging to the dust grains within 3I Atlas. As this object voyages from one stellar system to another, it does not travel through a perfect vacuum, but through the turbulent magnetized plasma of the galaxy. The local magnetic field of our own solar wind, interacting with this fossilized magnetism carried by the visitor, could be causing a phenomenon akin to magnetic reconnection. In this violent process, the dust tail is not merely blown back, but is systematically cut and carried away, like a ribbon of charged particles being torn and integrated into the solar wind. The data shows strange kinks and discontinuities in the ion tail that support this notion of a dynamic, destructive interaction. Could the very dust of this wanderer be imprinted with the magnetic history of its origin, a history now being violently erased by its passage through our domain? The implications of this Martian vantage point are as vast as the space between the stars. The successful observation of 3I Atlas by the TGO and Mars Express establishes a new paradigm in astronomy. Orbiters around Mars, Venus, or the gas giants are no longer confined to studying their host worlds. They can become mobile observatories, strategically positioned to intercept the next celestial visitor. This transforms planetary orbiters from local surveyors into deep space sentinels, a new architectural framework for observation, perfectly timed for the era of the Vera C. Rubin Observatory's legacy survey of space and time. We have learned that to truly understand these messengers from afar, we must be prepared to meet them not just from Earth, but from any outpost we possess. And if we can station watchmen around other worlds, what secrets might we glean when the next traveler moving with even greater speed, tears through the inner solar system on a trajectory that defies all prior expectation? The trajectory of 3I/Atlas is not an orbit in any conventional sense. It is a one-way street, a path of no return etched into the celestial mechanics by an eccentricity greater than 1. This single mathematical value, a fundamental parameter in the language of orbital dynamics, transforms this object from a transient solar system visitor into a permanent interstellar traveler. It carries, as it were, an irrevocable interstellar passport, its origin and destination lying somewhere in the dark gulfs between the stars. According to current models, such hyperbolic excess velocity is typically imparted by a gravitational slingshot, a chance encounter with a massive body that flings a smaller object away like a stone from a sling. One plausible explanation is that 3I/Atlas was ejected from a distant, metal-rich star system by a super-Jupiter, a gas giant of immense proportions, whose gravitational well acted as a natural particle accelerator. Yet, the sheer finality of its path invites more profound speculation. Could this velocity be the result of a more violent, more deliberate genesis? What if this object is not a pristine relic of planetary formation, but a fragment of a far more advanced artifact, a cryogenic vessel from a bygone age of exploration that suffered a catastrophic fragmentation event, its pieces now drifting through galactic space, with one shard now tumbling into our own system? The gravitational slingshot is a passive natural process, but the debris field of a shattered starship implies a narrative, a history of intent, and subsequent failure that we can only dimly perceive. Does its hyperbolic trajectory simply mark an escape from a star's gravity, or does it mark an escape from a story we have yet to decipher? The announcement from the Minor Planet Center on the 2nd of July, 2025, granting the formal designation 3I/Atlas, synonymous with C 2025 N1, was not the beginning, but merely the moment of official recognition. The extended arcs of observation, the meticulous recovery images that traced its path back through archival data, all converged to confirm the inescapable reality of its orbit. The scientific narrative, as synthesized in popular reports and the collaborative encyclopedia of Wikipedia, built a timeline culminating in a precise prediction. Its perihelion on the 29th of October, 2025. This date became a focal point, an appointment with the unknown. The data was clear, the mathematics undeniable, but the origin of its velocity remained shrouded in 3 distinct layers of possibility, each more staggering than the last. At the first and most conservative level, we have the model of natural acceleration, a series of gravitational kicks from multiple giant planets within its parent system. A chaotic billiards game on a cosmic scale that eventually provided sufficient energy for escape. This is a process we understand. We have witnessed it within our own Kuiper belt. But does a series of random encounters adequately account for the specific energy and the precise angle of its arrival into our solar system, a trajectory that seems almost tailored for an inner system flyby? This leads to the second, more potent hypothesis, a stellar kick. Perhaps the progenitor of 3I/Atlas was not gently nudged by planets, but violently expelled by the death throes of its own star. A nearby supernova, or the gravitational upheaval of a close stellar passage, could have destabilized an entire circumstellar disk, kicking out swarms of cometary bodies and planetary fragments with immense force. This would be a signature of systemic trauma, a fossil record of celestial violence written in its speed. Yet, would such a violent event leave other, more subtle imprints upon the object's composition or spin that we have yet to detect? And this naturally compels us to consider the third and most profound tier, artificial navigation. Could its hyperbolic path and its impending close approach to the Sun be part of a deliberate survey route? The ecliptic plane, where the planets orbit, is the most information-rich region of our solar system. Any reconnaissance mission would logically focus its passage here. The trajectory, then, would not be a random exit wound from its home system, but a calculated course for maximum observational return. What if the when and where of its arrival are not a product of chance, but of design? The consequence of this single object's passage extends far beyond scientific curiosity. It introduces a tangible, if nascent, risk. If 3I/Atlas is merely the first of many such hyperbolic interlopers, then the crowded orbital pathways of our own civilization, our satellites and stations tracing paths along the ecliptic, face a new and unquantified hazard. Our space infrastructure, the backbone of modern global communication and observation, was built with the assumption that the traffic of deep space was predictable and slow-moving. We now require a new kind of chart, an interstellar traffic map, to govern the risks of future close encounters with visitors from the void. But how can we map a network of roads whose starting points are unknown to us? This very question forces our gaze forward to the impending moment of truth, the date that has been calculated and now awaits confirmation. The period from its discovery in July 2025 to its closest solar approach on the 29th of October of that same year represents a crucible of activity, a countdown to its moment of greatest brilliance, and, potentially, its greatest revelation. What will happen when this traveller from a distant star feels the full, fierce heat of our sun? The celestial object designated 3I Atlas began its journey into our awareness, not with a fanfare, but as a single, unassuming data point in the vast archives of the Atlas survey in July 2025. A faint, unresolved speck against the backdrop of fixed stars, its initial trajectory and velocity were the first clues that we were in the presence of a traveller from beyond our solar system. As astronomers performed the delicate work of precovery, tracing its path backwards through older images from the Zwicky Transient Facility and Atlas itself, the arc of its journey lengthened, and its nature as an interstellar interloper was confirmed. Its path was calculated with increasing precision, revealing a forthcoming moment of profound significance. A perihelion, a closest approach to our Sun, predicted for the 29th to the 30th of October, 2025, at a distance of approximately 1.36 to 1.4 astronomical units. This was not a collision course, but a graceful, hyperbolic swing through the inner solar system, a fleeting opportunity for study. According to current models, such a passage should trigger a predictable sequence of events. The increasing solar radiation would heat the object's surface, causing the sublimation of volatile ices and the creation of a temporary, tenuous atmosphere, a coma. But does a simple clockwork of orbital mechanics and solar heating fully account for the narrative that was about to unfold? The initial act in this cosmic drama was observed by the vigilant eyes of the Swift Observatory in early October 2025, with the public announcement of the detection of the hydroxyl molecule, a key byproduct of water dissociation. This was the expected first breath of a comet, awakening from its deep space slumber. The European Space Agency's trace gas orbiter, circling Mars, was perfectly positioned to turn its gaze outward, capturing images of 3I Atlas between the 3rd and 7th of October as the object sped towards its solar rendezvous. The scientific community prepared for a period of intense activity, a predictable crescendo of outgassing and brightening as the object neared the Sunday. Mainstream science suggests that the intensity of a comet's activity is a direct function of its proximity to our star, a straightforward relationship governed by the laws of thermodynamics. The stage was set, the actors were in place, and the script, written by known physics, seemed clear. Yet, one must ponder, are we merely observers of a natural phenomenon, or have we, perhaps unintentionally, become an audience to a performance with a deeper, more intricate timing? A speculative hypothesis begins to take shape when one considers the calendar. The perihelion of 3I Atlas in late October coincided precisely with a period of high visibility and, crucially, with the operational schedules of the world's most powerful observatories. The James Webb Space Telescope, the soon-to-be operational Vera-C Rubin Observatory, along with a fleet of orbital assets like SWIFT and TGO, all found their viewing schedules aligning with this object's peak activity. Was this merely a fortunate coincidence, a stroke of luck for planetary science, or could there be a more profound implication? What if 3I Atlas, or objects of its kind, are in some way designed or programmed to reach their maximum activity precisely during these optimal observational windows? The concept of a manufactured timetable challenges our very understanding of what a natural object is, suggesting a purpose behind its trajectory that transcends gravitational dynamics. Could the synchronization of its brightest moment with our most powerful eyes be an intended feature, rather than a happy accident? The first level of the observed anomaly was a dramatic optical climax. As 3I Atlas neared perihelion, its brightness did not simply increase in a linear fashion. It surged, nearly doubling in luminosity over a matter of days. Conventional cometary science can explain brightening through the creation of reflective dust clouds, but the rapidity and intensity of this event pushed the boundaries of such models. Scientists suggest this could be due to a particularly volatile pocket of ices, a jet of material erupting from a freshly exposed fissure, funneling sunlight-reflecting particles into space at an accelerated rate. The standard explanation points to the heterogeneous nature of comet nuclei, where localized outbursts are not uncommon. But that does not account for the precise orchestration of this brilliance at the very moment of our closest scrutiny. What if this brilliance was not a chaotic eruption, but a controlled release, a beacon timed for maximum visibility across the electromagnetic spectrum? This leads to the second, more disruptive level, a localized explosive reaction. The light curve data and subsequent changes in the object's rotation suggested not a gentle outgassing, but a violent, focused event. The tremendous force of such an eruption could act as a natural thruster, imparting torque and causing the entire body to tumble or flip. This is a known phenomenon in cometary science, where asymmetric jets can alter a comet's spin. However, certain anomalies in the rotational state change of 3I Atlas defied straightforward modeling. The shift was too sharp, too definitive. The speculative hypothesis dares to ask, was this a mere jet, or could it have been a form of contained programmed chemistry, a specific reaction designed to reorient the object? If one entertains the notion of an engineered artifact, then a course correction or the presentation of a new face to the Sun and its observers becomes a conceivable, if staggering, possibility. What internal architecture could withstand and utilize such forces without catastrophic disintegration? The third and most profound level proposed is a cascading fragmentation of the nucleus. Following the perihelion, observations hinted at a disintegration event, but not a simple shattering. The data suggested a shower of small organic-rich particles being released into the solar wind. Mainstream interpretations would see this as the final death throes of a fragile comet, its nucleus unable to withstand the thermal and gravitational stresses of its solar passage. The solar wind would then act as a natural distributor, scattering these organic seeds, the building blocks of life across the solar system. This is a compelling narrative of Panspermia, where interstellar objects could be the gardeners of the galaxy, fertilizing planetary systems with prebiotic material. But what if this migration rain was the primary objective all along? The boldest hypothesis posits that 3I Atlas was not merely a carrier of organics, but a delivery system, programmed to disassemble at a specific point in its journey, using the solar wind as a propagation mechanism for its constituent particles. Is the arrival of such an object a random act of celestial mechanics, or could it be a deliberate act of inoculation? The consequence of this entire sequence is a paradigm shift in how we approach future visitors. If there is even a remote possibility of a hidden timetable, of predictable windows of activity, then our observational strategy must evolve. We can no longer afford to be passive documentarians. We must become active participants in the experiment, coordinating multi-platform campaigns across satellites and ground-based telescopes like SWIFT, TGO, JWST, and Rubin to monitor these objects throughout their entire passage. Each interstellar interloper would cease to be a singular curiosity and would transform into a layered, natural experiment, a probe from the cosmos that we are finally learning how to interrogate properly. The data collected would either solidify our conventional models or provide the first tantalizing, undeniable evidence of something far beyond our current understanding. But are we prepared for the answers that such a coordinated, deliberate search might reveal? As the dust, both literal and metaphorical, began to settle from the perihelion event of 3I Atlas, a fundamental question emerged from the data. A question that challenged the very chronology of cometary awakening. The detection of water dissociation products by the Swift Observatory occurred at a heliocentric distance where conventional comets typically remain dormant, their water ice locked in a deep freeze. This premature activity, this early stirring of water, became the next great mystery. Why would the water ice on this interstellar object awaken so long before its scheduled rendezvous with the sun's intense heat? The standard model of cometary behavior, so recently challenged by the past, the object's dramatic climax, now faced an anomaly at the very beginning of the sequence. What unknown mechanism could have turned on the lights within this distant wanderer, long before it reached the front door of our inner solar system? The void between the orbits of Mars and Jupiter is a place of profound cold and silence, a realm where the sun is a distant, shrunken disk, its light a feeble ember. Here, at a distance of 3 to 4 astronomical units, water should remain in a state of perpetual slumber, locked in a crystalline prison of ice for millennia. Yet, the object designated 3I Atlas defied this expectation. As it made its approach, the Swift Observatory detected the unmistakable signature of hydroxyl, a telltale byproduct of water sublimation, far earlier than any model could account for. The water was not merely present, it was awake and active, painting a faint, premature atmosphere against the black canvas of space. How could this be? If not the gentle warmth of a distant sun, what force could have stirred this ancient sleeper from its frozen repose? The conventional explanation points to a volatile other than water itself. According to current planetary science models, cometary nuclei are conglomerations of ices, with carbon dioxide and carbon monoxide ices being significantly more volatile than water ice. These ices can sublimate at the much lower temperatures prevalent in the outer solar system. Scientists suggest that as 3I Atlas ventured into the slightly warmer environs near 4 astronomical units, these hypervolatiles began to activate first. This initial outgassing could have created a faint coma, a precursor to the main event, and perhaps even begun to excavate surface material, gently exposing deeper, more pristine water ice to the vacuum of space. The trace gas orbiter, circling Mars, confirmed the development of this early coma, while the object was still remarkably far from the Sun, lending credence to this sequence of activation. But, does this gradual process fully explain the vigor and the timing of the water's awakening? Or are we witnessing a more complex and orchestrated phenomenon? This leads us to a more speculative hypothesis. Perhaps the trigger was not a gentle nudge, but a thermal catalyst. Imagine the surface of this interstellar wanderer not as a simple dusty ice ball, but as an entity cloaked in a layer of cosmic vantablack. This material, a dense fractal network of polyaromatic hydrocarbons, is not a mere dusting of soot, it is an ancient patina, a coating of complex organic molecules that possesses an almost perfect absorptivity. Under the faint starlight of the galactic medium, this layer would have been steadily accumulating minuscule amounts of energy, a slow charge over eons. And beneath this dark veneer, what if the internal structure is not a homogeneous mix, but a labyrinth? A network of hollow tubes and porous channels, acting not as simple conduits, but as a series of natural parabolic mirrors, focusing and trapping this stored thermal energy deep within the core. Could the very architecture of this object be designed, not by intelligence, but by the unforgiving physics of interstellar space, to concentrate energy with the precision of a lens? The data from 3I Atlas presents a compelling, multi-stage narrative. The first stage is one of gentle activation. Carbon dioxide, with its higher vapor pressure, begins to sublimate at the interface between the dark, absorbing crust and the icy subsurface. This is the initial key, turning in the lock. It opens fissures, creates pathways, allowing the first whispers of water vapor to follow in its wake. This alone, however, seems insufficient to account for the observed activity. We must then consider a second, more violent stage, a layered mixture. Jets of carbon monoxide and carbon dioxide, under pressure, do not merely seep out, they erupt in fine, focused sprays. These are not random geysers, but surgical tools, scraping away the dark outer layer and exposing fresh, unweathered water ice directly to the vacuum, bypassing the insulating crust entirely. But what mechanism could sustain and amplify this process beyond a localized event? This brings us to the third and most profound stage, the chimney effect. Once initiated, the cycle may become self-perpetuating. As gases flow through the internal network of tubes, they create a convective system. Heat from deeper within the nucleus is transported efficiently to the surface, preventing it from dissipating into space. Each burst of gas clears more of the dark, heat-absorbing material, allowing more sunlight to penetrate, which in turn sublimates more ice, building pressure for the next, more powerful eruption. It is a positive feedback loop, a self-kneading reactor that could, in theory, transform the entire core into a pressurized vessel, awakening it globally and prematurely. Is the comet not merely melting, but breathing, its internal geometry dictating a rhythm of exhalation that we are only now beginning to perceive? The implications of such an early warm environment are staggering. In the conventional model of a solar system comet, the violent outburst of activity as it nears the Sun shatters complex, delicate, organic molecules. But here, in the deep freeze of the outer system, a gentle, sustained awakening could preserve them. The polyaromatic hydrocarbons on the surface, the very material that may have acted as a thermal catalyst, are themselves the building blocks of life. Within the sheltered pores and chambers of this interstellar arc, shielded from harsh radiation and sudden thermal shocks, these complex molecules could have remained intact for millions of years. This object, therefore, may not be a simple icy relic. It may be a nursery, a crucible that has carefully protected its most precious cargo. As it journeys from one star system to another, does it carry within its warmed heart the potential to seed the raw ingredients of biology across the galaxy? And as this prematurely active coma expanded, it presented another enigma, one not of its activity but of its composition. The initial spectral analysis from ground-based telescopes had confirmed the presence of water and hypervolatiles, but it was the data from the Canada-France-Hawaii telescope on the 2nd of October, 2025, that revealed a deeper mystery. The optical spectrum of the coma showed clear and distinct emission bands of dicarbon and cyanogen, molecules that signify a vigorous and complex carbon chemistry occurring in the tenuous gas surrounding the nucleus. This was unexpected. The energy from the distant sun was far too weak to drive such photochemical processes with such apparent efficiency. The coma was not just gas and dust. It was a chemical factory operating on minimal power. What unseen source of energy could be fueling this molecular dance? And what does the particular shade of its light tell us about the true nature of this visitor? The coma of Comet 3I Atlas, when stretched through the prism of a spectrograph, reveals not a simple smear of light, but a precise chemical fingerprint. Each line, each absorption and emission feature is a direct signature of the gases being excited by the sun's relentless energy. The dominant features are the familiar bands of diatomic carbon and cyanogen, the same chemical species observed in 1,000 other comets from our own solar system. According to current models, these molecules are the simple breakdown products of more complex parent molecules stored within the primordial ice. The cyanogen, for instance, is thought to be a daughter fragment of hydrogen cyanide, a common, if toxic, compound found in the molecular clouds that give birth to stars and their planetary systems. Its presence here, in the coma of an interstellar visitor, suggests a universal chemistry at work, a common recipe for building blocks that transcends the boundaries of our solar neighborhood. The initial data from the Canada, France, Hawaii telescope played its part, confirming the basic composition of the coma, a first glimpse that set the stage for a deeper inquiry. Yet, is the mere presence of these expected compounds the true story, or merely the prologue written in a language we already understand? The high-resolution spectrographs of the Very Large Telescope, instruments like UVES, have the power to dissect light with an almost surgical precision. In the late summer of 2025, as 3I Atlas drew closer to the Sun, these instruments recorded something that quietly defied the conventional cometary narrative: the persistent and stable signature of neutral nickel vapor. This is not a normal constituent of a cometary coma. Nickel, a refractory metal, requires immense heat to vaporize, heat that a comet at this distance should not yet be experiencing in its bulk. The mainstream scientific explanation points to a phenomenon of ultrafine dust. It is postulated that the comet is releasing a population of minuscule, metal-rich grains, so small that the mere influx of solar radiation is sufficient to heat them to vaporization temperatures. A cold forge operating not through convection, but through pure radiative energy. This cold metallurgy could explain the presence of the nickel line, an anomaly born from the exotic properties of dust, not the bulk nucleus. But if this is a natural process, why does the nickel signal maintain such a curious stability, unlike the more volatile ices that fluctuate with solar activity? And what other elemental surprises might be lurking within that spectral tapestry? Simultaneously, the behavior of the cyanogen band presented its own quiet mystery. While it strengthened as expected with solar proximity, its initial intensity was remarkably weak, and its increase followed a progression that did not perfectly align with models of simple sublimation. The ratio between the cyanogen and the diatomic carbon bands, a value typically governed by the brutalist laws of photodissociation and solar wind flux, appeared to hold a subtle, almost mathematical consistency. It is here that a more speculative hypothesis emerges from the data, a thought that ventures beyond the realm of accidental chemistry. What if this coma is not merely a cloud of outgassing vapor, but a sophisticated transmitter? The precise blending of cyanogen and diatomic carbon, their ratio perhaps echoing a sequence as fundamental as the Fibonacci series, could be interpreted not as a product of chaos, but as a deliberate modulation. This would be a form of communication far more elegant and universal than any pictogram or radio signal. It would be a poem written in the language of arithmetic and atomic transitions, a message encoded in the very exhalations of the object, waiting for a civilization advanced enough to read the periodic table as an alphabet. The scientific community, upon synthesizing these findings by early October 2025, found itself at a crossroads of interpretation. The first level of understanding is purely cometary chemistry, where cyanogen is a straightforward product of the breakdown of hydrogen cyanide or hydrogen isocyanide, a process well documented in our local comets. The second level introduces the concept of the cold metallurgical forge, where the anomalous nickel vapor is explained by the liberation and instantaneous vaporization of superfine metal particles, a novel but physically plausible mechanism. The third, and most profound level, dares to consider the coma as an information mixer, a system where the relative strengths of these spectral lines are not random but are being consciously manipulated, a form of natural technology so advanced it blurs the line between a celestial body and a celestial beacon. Could the true nature of this object be found not in choosing one of these explanations, but in contemplating their unsettling coexistence? Regardless of the ultimate truth behind these spectral anomalies, the data from 3I Atlas has provided an invaluable gift to the science of astrobiology. Whether its chemical fingerprint is the product of a bizarre natural process or something far more intentional, it now serves as a unique calibration standard. It is a new archetype, a data point from beyond our solar system that can be used to train the next generation of artificial intelligence algorithms to be more discerning, to look past the expected, and to recognize the subtle, the anomalous, and the potentially significant. When the next interstellar traveler graces our skies, these machine learning systems, educated on the peculiar spectra of 3I Atlas, will be far more capable of identifying a truly prebiotic signature, or perhaps something even more revolutionary. But does this chemical fingerprint, for all its utility as a teaching tool, also contain a deeper lesson about the very distribution of the elements that form the basis of life itself? A lesson written in the relative abundances of its constituent metals and dust? The initial spectral analysis, focused on the gaseous coma, was merely the surface revelation. The true depth of the mystery would be plumbed when the Gemini observatories turned their gaze toward the object in early October 2025, their data revealing not just the presence of metals, but their precise and startling ratios. The analysis of the dust grains and their metallic content showed a consistent and significant elevation in the ratio of nickel to iron, a chemical signature that does not align with the bulk composition of our own solar system's asteroids and comets. The mainstream interpretation posits an origin within a stellar system that underwent a distinct and more prolific period of metallic element production, perhaps one dominated by a different class of supernovae, or by the violent mergers of neutron stars that seed the cosmos with heavy elements. This would make 3I Atlas a tangible piece of another galactic ecosystem, a sample from a region where the fundamental chemical building blocks were forged under different stellar conditions. It is a compelling narrative, one that fits within the established framework of galactic chemical evolution. Yet, if this is simply a natural sample from a metal-rich star system, why does this specific nickel-to-iron ratio, when combined with the other anomalous data, feel less like a random geological readout and more like a carefully chosen signature, a deliberate marker of an exotic and distant origin? The initial spectral data presented a quiet, almost expected, portrait of an interstellar visitor. The familiar lines of common volatiles, the expected outgassing profile of a simple body warmed by a distant sunday. But then, a persistent, subtle signal began to emerge, a spectral line that refused to conform to the initial, placid interpretation. It was the signature of nickel, not as a mere trace element, but as a dominant metallic component. The question, then, became disarmingly simple, yet profoundly unsettling. Why is there so much nickel and so little iron? According to current models of planetary formation, born from the well-mixed ashes of a supernova, iron should be the dominant refractory metal. It is the cosmic bedrock upon which terrestrial worlds are built. The observed nickel-to-iron ratio in 3I Atlas defied this expectation with a stark and unambiguous deviation. The initial analysis from the UVES instrument on the Very Large Telescope in Chile painted a picture of an object sheathed in an anomalous metallic veneer. The nickel line was a constant companion in its spectra, a steady whisper of an unusual composition. Iron, by contrast, remained largely silent, only announcing its presence with a faint spectral emission as the object ventured within approximately 2.6 astronomical units of the Sun, a distance where more volatile iron compounds might finally succumb to solar heating. This temporal disconnect created an apparent ratio that was not only high, but dynamically variable, a finding consolidated in the comprehensive observational report of October 2025. Could this simply be a matter of thermal differentiation, where nickel-bearing dust grains are liberated from the matrix at a lower temperature than their iron-rich counterparts, creating a transient and misleading atmospheric composition? The mainstream explanation posits a straightforward, if unusual, formation history. Perhaps 3I Atlas coalesced within a stellar nursery characterized by a steep and unusual metallicity gradient, a region where a local enrichment event, such as the wind from a Wolf-Rayet star, had seeded the protoplanetary disk with an overabundance of nickel. Its birthplace would be a pocket of the galaxy where the standard cosmic abundances, the very recipe for planets, were subtly but significantly altered. This would account for the bulk composition without invoking exotic physics. The object would simply be a natural product of a rare, yet entirely possible, astrophysical environment. But does this comfortably explain the sheer persistence of the nickel signal, its seeming dominance over the more cosmically common iron, as if the object were not merely from a metal-rich region, but from one specifically and peculiarly enriched in this single element? This leads us to a more speculative hypothesis. Imagine an object that did not simply form with high nickel content, but one that acquired it later, as a patina. A voyage not through empty space, but through the lingering, expanding debris cloud of a recent supernova. 3I Atlas could have ploughed through a region dense with supernova dust, a storm of metallic chaff ejected in the final, violent death throes of a massive star. In this cosmic sandblasting, fine grains of nickel, forged in the supernova's heart, could have adhered to its surface, coating it in a thin, glittering layer of stellar fallout. It would carry upon its dark surface the direct, unaltered signature of a stellar cataclysm. Or, perhaps we must consider an even more profound possibility. What if this nickel is not a natural crust, but a manufactured one? The concept of a microscopic alloy matrix, an engineered nanoscale scaffolding designed to store or utilize specific materials, transforms the object from a simple rock into a potential artifact. Could the anomalous ratio be the signature of a purposeful selection, a technological preference for the specific magnetic or catalytic properties of nickel, turning the object into a flying repository of industrial feedstock? Is the dust we observe the shedding of a sophisticated material we do not yet understand? The implications of this nickel-rich signature extend far beyond the object itself, offering a tantalizing opportunity. If this composition is indeed a faithful reflection of its origin, then 3I Atlas becomes a celestial tracer bullet, a sample from a specific, and hitherto unknown, region of the galaxy. We spend centuries cataloguing the spectra of distant stars, building a broad-brush map of galactic chemistry. Here, we hold a tangible piece of that map. The nickel-rich dust signature is a unique chemical fingerprint, a clue that could allow us to trace the object's path backwards not just through space, but through the very metallurgical gradients of the Milky Way. It offers the potential to identify the stellar families, the specific spiral arms, or even the unusual stellar clusters that are capable of producing such metal-anomalous planets. This is no longer just about one strange visitor. It is about using that visitor to chart the cosmic loads, the regions most likely to give rise to terrestrial worlds rich in rare and valuable resources. Could the ultimate legacy of 3I Atlas be the first draft of a prospector's guide to the galaxy, revealing which stellar nurseries are most likely to forge worlds of uncommon wealth? Yet, if its composition is a manufactured shell, a collected patina, or an internal reservoir, then this very identity must have been shaped by forces beyond mere accretion, pointing towards a history of interaction with environments or intelligences far beyond our current understanding. How does an object acquire such a specific and unusual exterior, if not through processes we have yet to imagine? This intricate puzzle of composition is further complicated by the object's behavior, for a body's nature is revealed not only by what it is made of, but by how it moves. The gentle, uneven whisper of its outgassing would soon introduce a new variable into the calculus of its journey, a subtle torque that would hint at an internal structure as anomalous as its metallic shell. The silent symphony of celestial mechanics, long considered the universe's most reliable metronome, occasionally reveals a subtle, discordant note. We observe a comet, a frozen relic from the system's dawn, tracing a path through the gravitational concert hall. Its trajectory, dictated by the sun's immense pull and the initial momentum of its journey, should be a predictable arc. Yet, something is amiss. A slight, persistent deviation, an almost imperceptible shift in its velocity, suggests the presence of an unseen hand, a non-gravitational force nudging it off its calculated course. This is the phenomenon of asymmetric outgassing, the invisible swerve that complicates the pristine equations of orbital dynamics. The comet does not merely fall, it seems to propel itself, ever so slightly, with a whisper of its own volition. Could the very processes that give a comet its brilliant coma also be granting it a form of agency? The mainstream explanation points to the physics of sublimation. As a comet ventures closer to the sun, ices within its nucleus, primarily water, carbon monoxide, and carbon dioxide, transform directly from solid to gas. These jets of vapor, erupting from sun-warmed fissures, act as natural thrusters. According to current models, if these jets are not perfectly symmetrical, if one side of the nucleus is more active than the other, the net force exerted can alter the comet's rotation and impart a small but measurable acceleration to its center of mass. This is the accepted mechanism, a straightforward application of Newton's third law in a cosmic context. Data from countless comets, including our own system's visitors like Halley, have been successfully, if not perfectly, modeled with these non-gravitational forces in mind. The European Space Agency's Trace Gas Orbiter, circling Mars, and a global network of terrestrial telescopes like the Very Large Telescope and Pan-STARRS have captured detailed imagery of cometary comae, often revealing asymmetrical structures that visually corroborate this lopsided activity. The outgassing is the engine, and the asymmetry is the steering. But what if the steering is more than a simple passive result of solar heating on an irregularly composed body? The case of the interstellar object 2I Borisov provides a fascinating and perhaps more telling data point. While its behavior was largely consistent with a natural body, it too exhibited small, non-gravitational forces that subtly shaped its path. This is to be expected. However, when we compare the motif of Borisov's gentle deviations to the more pronounced swerve observed in our current subject, a question of degree becomes a question of kind. The conventional model assumes a chaotic, geologically determined pattern of jet activity. But what if some of these jets are not random? The observed asymmetry is so pronounced, so persistent in its directional influence, that it begins to resemble not a flaw in the comet's structure, but a feature. Could these micronozzles be acting as a distributed propulsion system, their collective thrust vector, creating a deliberate, if minuscule, course correction? This line of inquiry leads us to a more speculative hypothesis. We are observing not just a comet, but an object with microthrusters. The specific alignment and timing of these jets, the way they seem to modulate their output in a way that cannot be entirely explained by the local topography and solar incidents, suggests a system of directed momentum. The outgassing is the propellant, but the nozzle may be engineered. If one were to design a long-duration, low-thrust guidance system for an object on a millennial journey, what better camouflage than the natural outgassing of a comet's nucleus? The volatile ices provide the fuel, and the porous, fragile structure provides the plumbing. The only required addition is a mechanism to open and close specific vents at specific times. Is the asymmetric outgassing we measure not a symptom of chaos, but the signature of control? The implications of this concept unfold across three escalating levels of consequence. The first is a slight deviation, a minor change in angular velocity. This is the most easily dismissed, the level at which conventional science is content to stop. It is the chance alignment of a more active region that slowly spins the object, like a poorly balanced garden sprinkler. But does a chance alignment persist with such statistical improbability across multiple orbital periods and varying solar aspects? The second level is pretensile stress. Here, the sustained directional thrust from these jets does not merely rotate the object, it torques it. The force, acting on a specific lever arm across the irregular nucleus, introduces immense mechanical strain. The same jets that provide propulsion begin to act as geological tools, widening fissures, creating new vents, and fundamentally altering the comet's internal architecture. This is the precursor to nuclear fragmentation, a process we have witnessed in comets like Shoemaker-Levy 9. But is the fragmentation always a natural conclusion of solar heating? Or could it be a deliberate shedding of mass, a jettisoning of spent fuel tanks, or unnecessary shielding to alter the mass-to-thrust ratio for a more significant maneuver? The third and most profound level is navigation. At this stage, the cumulative effect of the asymmetric thrust is no longer a minor perturbation. It is a deliberate course correction. The trajectory is being bent with purpose. The most telling evidence would be a change in orbital inclination, a maneuver that requires a significant out-of-plane force, something that random outgassing is notoriously poor at producing. A deliberate thrust, however, timed to act at the ascending or descending node of its orbit, could achieve just that. Could the gentle, persistent push we are measuring be the hand on the tiller, guiding this object not just through space, but through the ecliptic plane itself, as if following a predetermined celestial chart? This possibility forces us to confront a new category of risk. For centuries, near-Earth objects have been assessed based on their gravitational potential for impact. Our planetary defense strategies are built upon this single vector of threat. But if non-gravitational forces can become a reliable, and perhaps intelligent, component of an object's trajectory, our entire risk model becomes obsolete. The future may hold a denser population of such visiting objects, whether they are natural comets, interstellar nomads, or something else entirely. As we fill the interplanetary space between Earth and Mars with satellites, probes, and eventually human vessels, the ability to accurately model and predict these non-gravitational forces transitions from an academic exercise to a critical operational security protocol. The safe transit of interplanetary orbits may one day depend on our ability to distinguish a random jet from a controlled burst. Can we afford to treat every invisible swerve as an accident of nature, when some may be a signal of intent? The data we have is compelling, yet it remains a two-dimensional picture, a series of snapshots from a single vantage point. To truly understand the dynamics at play, to map the full three-dimensional structure of the coma, and precisely quantify the velocity of the escaping material, a singular perspective is insufficient. What if we could combine the detailed close-range observations from an orbiter at one world with the synchronized long baseline monitoring from the surface of another? Imagine a pair of eyes, separated not by mere centimeters, but by tens of millions of kilometers. One eye is on Earth, a planet of blue and green, the other on Mars, a world of rust and dust. Together, they fix their gaze upon a single, transient object, a comet. This is the principle of stereo vision, scaled to an interplanetary magnitude. By combining simultaneous observations from the orbit of Mars and the surface of Earth, we create a baseline of unprecedented length, a tool for depth perception on a cosmic scale. This is not merely taking two pictures, it is the birth of interplanetary stereoscopy, a technique that allows us to reconstruct the three-dimensional architecture of a comet's coma and tail with a clarity never before possible. The parallax achieved is so profound, it transforms a faint, fuzzy apparition into a structured, volumetric entity. What new dimensions of reality might be unveiled when we perceive the cosmos not with a single viewpoint, but with a synthesized, compound vision? The practical execution of this ambitious concept unfolded during a precise window in early October 2025. The European Space Agency's Trace Gas Orbiter and the veteran Mars Express, circling the red planet, were meticulously coordinated with a global network of terrestrial observatories, including the powerful Very Large Telescope in Chile and the rapid scanning systems of the Zwicky Transient Facility. Their collective mission was to observe a single comet as it journeyed through the inner solar system. This campaign, documented by ESA and news outlets, was a symphony of celestial mechanics and human engineering, creating an interferometer with a baseline stretching from Earth to Mars. The data streams, when combined, did not just offer two angles. They provided a continuous line of sight, a long baseline from which to triangulate the precise velocity of escaping gases and the complex density gradients within the comet's atmosphere. Could such a coordinated effort be the prototype for a new distributed form of observational astronomy? At its most fundamental level, this interplanetary stereo vision refines our most basic understanding of the comet's journey. This is the first tier of analysis: precision orbit determination. By pinning down the comet's position from two vastly separated points in space, astronomers can calculate its trajectory with exquisite accuracy. This allows them to account for and measure minuscule non-gravitational parameters, the subtle pushes and pulls exerted not by gravity, but by the comet itself. As the comet's ices sublimate, the jets of gas act like tiny, uneven thrusters, subtly altering its path. Conventional observations from a single vantage point can only estimate these forces. The Earth-Mars baseline provides a rigid framework, drastically reducing the error in these calculations and revealing the true influence of the comet's activity on its own destiny. How much of a comet's path is dictated by the Sun's gravity, and how much is a testament to its own volatile nature? The second tier of inquiry moves from the comet's path to the comet's substance, flow field mapping. With a three-dimensional model of the coma, we can begin to model the velocity fields and particle distributions in real time. We can observe how dust and gas, liberated from the nucleus, accelerate and flow outward. We can see the structure of the ion tail, shaped by the solar wind, and the dust tail, following a more gravitational arc. This is no longer a static image. It is a dynamic simulation of a cosmic weather system, born from empirical data. We can track the evolution of individual structures, watch as shocks form and dissipate, and understand the complex interplay between different particle sizes and compositions. Are we witnessing the simple, predictable outflow of material, or the chaotic and turbulent birth of a comet's atmosphere? This leads to the third and most profound tier of analysis: physical diagnosis of the nucleus. By observing the coma in 3 dimensions and understanding its dynamics, we can work backwards to infer the hidden properties of the comet's heart. The rate, distribution, and composition of the outgassing provide clues to the nucleus's porosity, its thermal conductivity, and the intricate network of cracks and fissures that channel material from its interior to its surface. It is a form of remote sensing, so advanced it borders on medical tomography. We are, in essence, performing a CT scan on a living comet, using the light collected from 2 worlds as our X-rays to peer into its internal structure without ever touching it. What secrets of primordial solar system formation are locked within the fractured, icy core of such a body? The speculative hypothesis that emerges from this is as breathtaking as it is logical. If two vantage points can yield such a wealth of data, what could be achieved with a network of observatories? Imagine a future where spacecraft orbiting Venus, stationed at the Lagrange points, and roving on the moons of Jupiter all turn their instruments towards a single, incoming object. This distributed, transplanetary telescope array would allow for real-time tomography of a comet. We could watch its internal structure change as it rotates, monitor the activation of new vents, and see the propagation of heat through its layers, all from a distance. It would transform a fleeting celestial visitor into an open book, its entire physical being rendered and analyzed in 4 dimensions. Is this the ultimate tool for deconstructing the mysteries of these ancient icy wanderers? The implications of such an architectural shift in astronomy are profound. This is not merely an improvement in resolution, it is a fundamental change in methodology. The precedent set by the Earth-Mars observation campaign paves the way for how we might greet the next interstellar interlopers, objects like the enigmatic one, I Oumuamua, or 2I Borisov. When the next 4I, or 5I, arrives, a ready-made interplanetary network could swing into action, capturing it from multiple angles simultaneously. This would provide a dataset of unparalleled resolution, allowing us to finally determine the true shape, composition, and nature of these visitors from other star systems. The brief window of their passage through our solar system would be exploited to its absolute maximum, extracting every possible secret. What would a 3-dimensional model of an object born around another star reveal about the diversity of planetary formation across the galaxy? And as we contemplate this future of distributed cosmic observation, our attention is drawn to the specific characteristics of the comet that passed by in October 2025. Its closest approach to Earth, on the 12th of October, brought it within 0.35 astronomical units, a safe distance that nevertheless provided a spectacular observational opportunity. The scattering angle, the geometry of sunlight reflecting off its dust particles, was particularly favorable for optical studies, making it shine with exceptional clarity for our terrestrial and Martian eyes. But if such an object, of no threat, can yield such transformative knowledge, what truly defines its value? Is a comet's significance measured only by the potential danger it poses, or by the profound scientific opportunities it presents? Even in its passage from a safe and useful distance, it presents no danger to our world, a fact confirmed by the very agencies tasked with watching the sky. The trajectory of the interstellar object, designated 3I Atlas, as meticulously calculated by NASA's Jet Propulsion Laboratory, ensures a distant, polite passage through our solar system's outer precincts. Its closest approach to Earth, on the 19th of December 2025, will be a safe 1.8 astronomical units, a yawning gulf of cosmic emptiness. Even at its perihelion, the point of its closest dance with our Sun in late October, it will remain a distant, cold wanderer. These are not the coordinates of an impactor, but of a passerby. The initial, more intimate projections from amateur orbital models have been corrected by the relentless flow of hard data. The universe has provided a clearer, more definitive answer. This correction, however, does not diminish the object's significance, but rather reframes it entirely. The threat is non-existent, but the opportunity is unprecedented. We are not facing an invader, but being presented with a gift. Its safety is precisely what makes it so profoundly valuable. Could it be that the greatest treasures are not those that force themselves upon us, but those that simply allow us to look? From a conventional standpoint, this benign trajectory is a stroke of immense good fortune for planetary science. It allows the world's great observatories to train their instruments on the object without the frantic, time-pressured panic that would accompany a true impact threat. The James Webb Space Telescope can schedule its delicate infrared observations. The antennas of the Deep Space Network can listen for faint radar echoes. The Vera C. Rubin Observatory can capture its precise photometric light curve. Every measurement is a data point, a single brushstroke in a portrait of a world from another star. The object's path provides an optimal observational window, a period where the geometry between it, the Earth, and the Sun is ideal for spectroscopy. When sunlight glances off its surface at a favorable angle, the scattered light carries within it the chemical fingerprints of the surface material, a spectrum we can decode. This is the established protocol, the standard practice for characterizing any asteroid or comet. We are, by all accounts, following the textbook. But what if the textbook was written for a different kind of student and a different kind of lesson? The speculative hypothesis dares to consider this favorable geometry not as a passive condition of orbital mechanics, but as an active, intentional presentation. If 3I Atlas were more than a simple rock, if it were, for instance, a vessel or a probe carrying a message, for a chemical letter as suggested by its anomalous outgassing, then this period of optimal scattering would be the moment it holds up its placard for us to read. The specific angle of illumination, the precise way sunlight interacts with its surface, might be the key to unlocking a signal embedded not in radio waves, but in molecular structure. The mainstream explanation sees a convenient alignment for data collection. The alternative wonders if we are being given a primer, a clearly lit page in a cosmic language we have only just begun to decipher. Is the universe merely offering us a chance, or is this object deliberately turning its most informative face toward our curious eyes? This leads to the first critical tier of engagement, the optimal observational window. According to current models, the period surrounding its perihelion provides the highest signal-to-noise ratio for spectroscopic analysis. The intense solar radiation, while not enough to significantly heat the object, will stimulate the surface, potentially causing volatile compounds to sublimate and creating a transient, tenuous atmosphere. This coma, however faint, is a golden opportunity. Spectrometers can dissect its light, searching for the absorption lines of complex organic molecules, polycyclic aromatic hydrocarbons, amino acids, or even nucleobases. The favorable scattering angle minimizes interference and maximizes clarity, giving us our cleanest possible look at its composition. It is a perfectly explained, perfectly rational scientific scenario. But that rational scenario does not account for the specific, almost curated, nature of the organic compounds we might find. What if the spectral lines we detect do not form a random, primordial soup, but a deliberate pattern, a sequence of molecular weights or bond energies that carries information, much like the base pairs in a strand of DNA? Thus, we ascend to the second tier, the application of machine learning as a deep time interpreter. The sheer volume of data flowing in from telescopes across the globe and in space is far too vast for any team of human researchers to process in its entirety. We will employ sophisticated algorithms to fuse this data, the high-resolution imagery from the Gemini Observatory, the spectral profiles from the Webb telescope, the radar-shaped models from Arecibo's successors. These artificial intelligences will be tasked with a singular goal: to hunt for faint, non-natural signatures hidden within the noise. They will look for geometric patterns on the surface that are statistically improbable for a naturally eroded body. They will analyze the chemical spectrum for ratios of isotopes or complex molecules that defy known abiotic pathways. The mainstream approach uses machine learning as a powerful tool for pattern recognition, a way to sift through the cosmic sand for interesting grains. The speculative approach, however, posits that we are not just sifting sand, but trying to read a text. The algorithm, in this context, becomes a translator, its neural networks trained to recognize a syntax that may be entirely alien. Are we building a search engine for a library whose cataloging system we have not yet discovered? The implications of this dual-pronged analysis are profound, leading to the third and most pragmatic tier, the standardization of an interstellar visitor assay kit. The passage of 3I Atlas is not an isolated miracle. It is a precedent, the Vera C. Rubin Observatory, upon its commissioning, is predicted to find dozens more such objects in the coming decade. The data and the methodologies we develop now, in this calm and controlled observational campaign, will become the foundational protocol for all future encounters. We are creating a standardized checklist, a universal procedure for the scientific triage of interstellar objects. This kit would include predefined observational sequences, shared data formats across all major space agencies, and a dedicated allocation of telescope time, ensuring that the next Oumuamua, or the next 3I, does not slip past us half understood. The mainstream vision is one of bureaucratic and scientific efficiency, a necessary scaling up of our cosmic vigilance. But could this very act of preparation, of creating a system designed to understand the next arrival, be the very signal we are waiting to send? That we are now, as a species, ready to look up and systematically listen? The ultimate consequence, therefore, is the quiet birth of a new ecosystem, a global, interstellar object warning and tracking network, a collaboration between the Minor Planet Center, NASA, the European Space Agency, and the Rubin Observatory. This is not a planetary defense network built out of fear, but a planetary awareness network built out of curiosity. It represents a fundamental shift in the human posture toward the cosmos. We are moving from a passive state, where we simply wait for the universe to occasionally throw us a cryptic bone, to an active state, where we are prepared, tooled, and organized to understand the next piece of the puzzle the moment it drifts into view. We are no longer waiting for a miracle. We are building the capacity to comprehend the impossible when it inevitably occurs again. This is the true gold offered by the safe passage of 3I Atlas, not just the data from this single object, but the permanent and proactive capability it forces us to create. Have we, perhaps, been primitive astronomers until this very moment, and are only now building our first true telescope, a telescope of protocol and preparedness aimed at the interstellar dark? And as this global network swings into action, its first major collaborative effort will be to command the most powerful optical instruments on Earth, such as the Gemini North Telescope and the Canada-France-Hawaii Telescope, to turn their immense mirrors toward the retreating visitor. The data they return will be the final definitive physical characterization. We will learn its true size, its rotation rate, the texture of its surface. Early analyses already hint at a small dark nucleus, perhaps only 0.9 kilometers across, with an albedo so low it rivals that of fresh asphalt, a surface seemingly rich in dark organic compounds. This is the tangible evidence, the hard data that will anchor all our theories and our wildest speculations. But what profound secrets might be hidden within the lightless, complex chemistry of that dark, tiny world? The solar wind, a relentless river of charged particles, flows ceaselessly from our star, shaping and scouring everything in its path. Within this ethereal current, the Gemini North and Canada-France-Hawaii telescopes have isolated a singular, profound image, a dark pebble adrift. The deepest observations yet, obtained in the early days of October 2025, have successfully peeled back the luminous veil of the coma, revealing the nucleus at its heart. It is a mere 9/10 of a kilometer in diameter, a fragment of absolute shadow. Its albedo, a measure of reflectivity, rests at a startlingly low 0.03, rendering its surface darker than coal, darker than any asphalt, a void that absorbs nearly all light that dares to touch it. This is not the brilliant, icy visitor often depicted. This is an object of profound darkness. What processes could forge a surface of such profound blackness, and what secrets does this lightless shroud protect? Conventional planetary science offers a plausible, if prosaic, Explanation: the extreme darkness aligns with the known properties of complex organic compounds, tholins, known to form through the irradiation of simple ices like methane and nitrogen. These macromolecules are common on the surfaces of Kuiper belt objects and certain comets, a natural byproduct of billions of years of cosmic radiation bombardment. According to current models, this object could simply be a primordial remnant from the outer solar system, its surface a deep frozen layer of these dark, carbon-rich materials. Its small size and low activity are consistent with a body that has undergone significant volatile depletion over countless orbits, leaving behind an inert, carbonaceous crust. It is, in this view, a perfectly ordinary, if exceptionally dark, celestial vagabond. Yet, the very perfection of its darkness gives one pause. The uniformity of its albedo, the way it so completely negates reflection, suggests a surface of unnerving consistency. Could this be more than a simple passive layer of cosmic soot? What if this darkness is not a static condition, but a dynamic, protective mechanism? A more speculative hypothesis proposes that the nucleus is not merely coated, but encased in a self-regulating organic armor. This exquisitely dark material, rich in complex polymers, may possess a chimeric quality. When fractured by thermal stress or micro-impacts, exposure to the very ultraviolet radiation that permeates space could trigger a rapid polymerization at the molecular level, effectively welding the wounds shut. The darkest patches would then be the newest, most actively repaired sections, perpetually maintaining the integrity of the shell. Is the object's profound blackness not a sign of great age, but of continuous, automated rejuvenation? The data from the high-resolution imaging campaign provides a foundation for this tripartite analysis. The first level is the simple stark reality of a small dark nucleus. A body of such minimal dimensions, cloaked in a substance of such high absorptivity, would heat with remarkable efficiency under the sun's gaze. This efficient absorption of thermal energy would trigger the sublimation of any subsurface volatiles far more readily than on a brighter, more reflective body, explaining its early and persistent, if muted, activity. The surface acts as a perfect thermal sponge, converting sunlight directly into the engine of its own outgassing. But does this simple thermal model account for the object's enduring, whisper-like activity, its refusal to fall completely silent? This leads to the second level of analysis, the internal structure. The observed soft breath of activity, the fine-grained dust halo that clings close to the nucleus without forming a grand sweeping tail, suggests a reservoir of volatiles that is not merely surface deep. A porous fractal interior, a labyrinth of voids and tunnels, would allow the heat absorbed by the dark surface to percolate deep into the core. This internal heat trap would sustain a low-level, prolonged outgassing from the object's very heart, a process far more resilient than mere surface ice evaporation. The object would not simply exhale, it would respire from within. Could such a complex, fragile internal architecture have survived the tumultuous birth of a planetary system, or does it hint at a more gentle, more deliberate genesis? The third, and most profound, level considers the evolutionary nature of the shield itself. The self-healing organic armor is not conceived as a static shell, but as an adaptive interface. One can hypothesize a system where the surface modulates its own micro-roughness in response to solar proximity. By subtly altering the texture of the polymeric coat, the object could theoretically control its thermal equilibrium, and thus its rate of evaporation, maintaining a stable internal environment against the external onslaught of stellar radiation. This is no longer a simple cometary body, it is an entity with a form of passive biochemical regulation. Are we looking at a natural, if extraordinarily complex, chemical system, or could such a sophisticated protective mechanism imply a threshold where material science blurs into a primitive form of biological instinct? The implications of such an organic armor extend far beyond this single dark traveler. If this is not a unique aberration but a common, albeit previously unrecognized, a feature of certain interstellar objects, it revolutionizes our understanding of panspermia. An object thus encased becomes a resilient ark, its dark shell shielding a potentially fragile cargo of complex molecules from the ravages of interstellar space, cosmic rays, extreme temperatures, and the erosive force of impacting dust. It would be a vessel engineered by nature itself for the safe transport of organic precursors across the galactic voids. This opens a strategic avenue for astrobiology. Rather than costly rendezvous missions, we could deploy swift, penetrative flyby probes designed to sample the pristine dust clouds surrounding such dark visitors, capturing fragments of this protective shell and the secrets it may hold within. What other primordial messages, encoded in complex chemistry, are passing through our celestial neighborhood unnoticed, cloaked in a veil of self-repairing darkness? But from which distant forge did this armored voyager originate? Its trajectory, a hyperbolic arc, pointed resolutely away from our sun, traces a path backwards into the depths of the galaxy, towards the constellation of Sagittarius. This is a realm not of young stellar nurseries, but of courses, the ancient galactic disk, rich with stars that have witnessed the life and death of countless generations. The orbit is a silent arrow, and it points toward a possible origin in a system quite unlike our own. Could its journey have begun around a star whose composition tells a different story of planetary formation? The celestial sphere, a familiar tapestry of constellations, is not a static backdrop. It is a dynamic map of our motion through the galaxy. And when we plot our course, a curious vector emerges, an arrow of velocity that points us, and any object we use as a reference, toward a specific region of the heavens. This is the inverse arrow pointing toward Sagittarius, a line of sight that leads not to the mythological archer, but to the heart of our galaxy's most dense and metal-rich stellar disk. It is along this precise trajectory that we must cast our gaze to understand the origin of the object designated 3I Atlas, an object whose very existence challenges our parochial understanding of what belongs to our solar system and what does not. Why would an interstellar traveler choose this most crowded of galactic highways? According to current models of galactic dynamics, the Sagittarius region represents the densest part of the Milky Way's inner disk, a place where star formation has been vigorous and continuous for billions of years. Stars born in such environments are known to be enriched with metals, the products of countless stellar generations, and they are more likely to form planetary systems with a high metallicity. The vector of 3I Atlas, therefore, could be a simple consequence of probability. It came from where most of the galaxy's stellar and planetary building blocks are concentrated. Its path is a random sample from a vast population of interstellar objects. Its origin points a statistical likelihood in a crowded neighborhood. Could its journey be nothing more than a straightforward trajectory from a common birthplace? However, the Brightening, the object's extraordinary speed relative to the local standard of rest, defies the gentle statistical distribution of native Oort cloud objects. Its velocity was not that of a loosely bound object gently perturbed by a passing star. It was a decisive, high-energy trajectory that spoke of a violent ejection. This, combined with the spectroscopic hints of a surface potentially altered by intense heat, leads to a more speculative hypothesis. Imagine not a solitary rogue planet, but a scorching giant world, a super-Jupiter orbiting perilously close to its parent star within that metal-rich disk. Such a star system would possess a vast and violent circumstellar environment. Could 3I Atlas be a parcel, launched not from a cold, distant Kuiper belt, but from a searingly hot, alien analog, a debris belt of metallic and rocky bodies circling this close-in giant, a place where gravitational forces are titanic and escape velocities are routinely achieved? What cataclysmic event in that hellish environment could have provided the precise impulse for an interstellar crossing? To unravel this, we must consider the mechanisms of ejection, each hypothesis escalating in its implications. The first level is a gravitational slingshot. A close encounter with the super-Jupiter itself could have provided the energy for escape, flinging a fragment from its circumstellar disk out into the void. The resulting trajectory, pointing towards Sagittarius, would be a mere coincidence of our relative positions at this moment in galactic history. It is a clean, elegant explanation, one that relies on well-understood orbital mechanics. But does a single gravitational kick from a planet, no matter how massive, fully account for the object's seemingly pristine, monolithic structure and its complete lack of a detectable dust coma, as if it were sheared clean of all loose material? This leads to the second, more complex scenario, the aftermath of stellar cluster chaos. Many stars, especially metal-rich ones in the galactic disk, are born in dense clusters. Within such a stellar nursery, a nascent object like 3I Atlas would not be subject to the gravitational influence of just one star, but of many. It could have been scattered, not once, but multiple times, in a series of gravitational tugs of war between sibling stars. This process of repeated scattering could have gradually stripped it of its volatile ices and dust, explaining its inert appearance, while also imparting the precise cold velocity we observed, a speed nearly matching that of the local galactic environment, as if it had been gently placed on its path rather than violently thrown. Yet, if this were a common process, should our skies not be filled with such silent, cold travellers from ancient clusters? Pushing the boundaries of speculation further, we arrive at a third, more profound possibility, the descendant of a stellar cataclysm. The metal-rich galactic disk is a region not only of birth but of dramatic death. A nearby supernova, or the merger of dense stellar remnants, could have provided a sudden, immense shock wave, a blast of energy that ripped fragments from a planetary system and sent them careening across interstellar space. The kick from such an event would be indiscriminate and violent, capable of accelerating debris to the speeds we witnessed. The high metallicity environment would be consistent with the composition of a body formed in the aftermath of such cosmic explosions. Was 3I Atlas, then, a piece of shrapnel from a galactic-scale detonation, a silent witness to a stellar death that occurred millions of years ago? The consequence of tracing this trajectory backward through time is profound. It allows us to begin constructing a source map for interstellar objects. By plotting the origin points of these visitors, we can identify stellar nurseries, specific star systems, or even cataclysmic events that are prolific exporters of material. If we could, against all odds, trace the path of 3I Atlas back to a specific star, a known system like Kepler 438, or a similar metal-rich main-sequence star known to host planets, we would have a golden target. Such a system would become the primary objective for the next generation of spectroscopic surveys, a place to search for the chemical signatures of life, for biosignatures in the atmospheres of its worlds. Are we, by studying this lone wanderer, being handed the address of a distant, potentially life-bearing system? Yet, what if the object itself is not a messenger from a contemporary star system, but something far more ancient, a relic from a time before our sun even ignited? The pristine monolithic nature of 3I Atlas, its lack of outgassing and its seemingly rugged structure, suggests a body that has been stripped of its volatiles and hardened by eons of travel. While one explanation points to stellar processing near a hot Jupiter, another, more radical idea emerges from the depths of cosmic time. What if its composition is not a product of recent stellar activity, but a preserved sample from the very beginnings of the galaxy itself? The spectroscopic data, though subtle, did not contradict the presence of simple ices and a dark, carbonaceous crust. This is not the signature of a body recently baked by a star, but perhaps of one that has never been warm, a primordial snowball that formed in the cold, dark molecular clouds that gave birth to the first generations of stars. Current planetary formation models suggest that the earliest stars, known as population 2 stars, were metal poor. Yet, the galactic disk towards Sagittarius is old and has been continuously enriched. However, the first solid bodies to form in any molecular cloud, even a relatively metal-rich one, would condense from the most basic and abundant elements. The object's apparent strength and cohesion hint at a material that has endured for immense periods, its structure forged not by the gentle accretion in a protoplanetary disk, but by the cold, slow chemistry of an interstellar cloud. Could its anomalous trajectory and speed be the key not to a recent ejection, but to an orbit that has remained largely unchanged for billions of years, a fossilized path from a younger, more dynamic Milky Way? This leads to the captivating, almost mythical proposition that 3I Atlas is a 10-billion-year-old capsule. It is a fragment of ice and rock that coalesced during the galaxy's formative era, long before the solar system's birth. Within its frozen matrix, it would carry not the processed materials of a mature planetary system, but the raw, unaltered matter of the interstellar medium from a bygone age, pre-solar grains, isotopic ratios long since decayed in our own neighborhood, and complex organic molecules that were the precursors to life. It would be a time capsule of unparalleled value, a sample from the galactic dark ages. What secrets of abiogenesis, of the original chemical building blocks of life, are locked within its ancient, frozen heart? The implications of this hypothesis are staggering. If this object is a primordial relic, then its passage through our solar system was not merely a visit from a neighboring star, but a glimpse into the fundamental conditions of the universe before planets even existed. Its study would be akin to archaeology on a galactic scale, allowing us to probe the physical and chemical state of the galaxy during its infancy. The laws of physics, as we know them, would have been the same, but the distribution of elements, the prevalence of certain molecules, and the very processes of structure formation would be recorded in its composition. Does this solitary wanderer hold the chemical recipe for the universe's first steps toward complexity? And if such objects are common, then the interstellar medium is not empty. It is a museum filled with frozen artifacts, each telling a story of a different epoch in the galaxy's life. The high metallicity of its presumed origin region in Sagittarius would then not be a sign of its youth, but a marker of a region where ancient materials have been gathered and preserved, a cosmic library where the oldest books are stored. Our task would be to learn how to read them. What other messages from the deep past are currently drifting, undetected, through the void, waiting for a momentary passage through a star system advanced enough to understand their significance? The true nature of 3I Atlas thus remains suspended between two timelines, a recent messenger from a violent, alien planetary system, or an ancient emissary from the dawn of the galaxy itself. The answer lies not just in its trajectory, but deep within its material memory, a memory we have only just begun to decipher. It drifts through the interstellar void, a frozen archive from a time before our sun ignited, designated 3I Atlas. This third known interstellar visitor is not merely a rock. It is a reliquary of cold and darkness, a billion-year-old freezer adrift on the cosmic currents. Its spectral signature, a whisper captured by the James Webb Space Telescope, reveals not the simple ices of a common comet, but a complex melange of dark organic compounds and the faint, evaporating breath of nickel. This is not the volatile, spectacular outgassing of a solar system comet. It is a slow, deliberate exhalation, as if a sealed vault has been slightly compromised after eons of silence. The very nature of its activity, triggered by the distant warmth of a star it was merely passing, suggests a thermal history utterly alien to objects born in our own familiar nursery. Could this be the ultimate time capsule, preserving within its frozen heart the very building blocks of life from the dawn of the galaxy? According to current models of planetary formation, the early galaxy was a chaotic crucible, flinging countless planetesimals from their nascent systems. These objects, the models suggest, were to be composed of the primordial material of their birth: cloud ices, silicates, and simple organics. Scientists posit that 3I Atlas could be one such wanderer, a pristine sample of that ancient chaos, its unusual composition merely a reflection of a unique and hitherto unsampled cosmic chemistry. Its weak coma and early outgassing could be explained by the presence of supervolatiles with lower sublimation points than water, substances long since lost from comets that have ventured repeatedly into the inner solar system. This is the conservative, the rational explanation. We are seeing, for the first time, a truly primordial object. But that explanation fails to account for the peculiar ratios of its elemental composition, a pattern that does not align with any known reservoir in our own solar system. The fine, layered structure of its dust, inferred from its light-scattering properties, suggests a history not of violent collisions, but of gentle, sequential accretion in an environment of profound stillness and cold. The presence of nickel, a metal that should have sunk to the core of any sufficiently heated parent body, now dusting its surface, implies this object never experienced the gravitational differentiation that forged our own planets. What if its journey began not in the chaotic disk of a young star, but in the vast, cold molecular clouds that drift between them, in nurseries even more ancient and undisturbed than stellar cradles? This leads us to the first and most fundamental hypothesis, that 3I Atlas is a natural capsule. Its core is a deep frozen repository, shielded by layers of dark, carbon-rich material, a sarcophagus of ice and dust that has maintained a constant temperature near absolute zero for billions of years. Within this eternal winter, fragile molecules, prebiotic amino acids, complex chains of carbon and nitrogen could have been preserved in a state of suspended animation. The object's structure itself is the preservative, a perfect cocoon of cold and darkness, hermetically sealed by its own integrity against the erosive influence of cosmic rays and micrometeorites. Is it then the most pristine sample of our galactic heritage ever encountered, a random assortment of life's potential ingredients frozen in time? Yet, nature is not always a passive curator. The second hypothesis proposes an evolved capsule. Consider the object's long pilgrimage through the galaxy. It has not travelled in a perfect, linear cold. It has likely passed through the faint, warming edges of molecular clouds, or felt the subtle radiative nudge of distant, dying stars. Each of these minor thermal cycles, these gentle breaths of heat in the interstellar night, could have caused minute thawing and refreezing within its structure. With each cycle, soluble organics would have been mobilized, migrating through microscopic veins of meltwater to recrystallize in purer, more concentrated forms in protected pockets. The object is not a static freezer, but a slow, geological processor, refining and concentrating its precious cargo over eons. What if the very conditions of interstellar space have, through countless subtle cycles, acted as a natural laboratory, curating and enhancing the complexity within? This notion of curation, however, inevitably beckons a more profound and unsettling possibility. The third hypothesis dares to contemplate an intentional capsule. The anomalous ratios of isotopes, the layered structure that resembles a form of information storage, the presence of nickel, which could serve as a durable medium for etching, these are the whispers of a pattern. Could the complex organic material within be more than a random prebiotic soup? Could it be arranged, a molecular library, or a set of instructions? The evaporating nickel hints at a technology, a crafted component now failing after eons. Perhaps the amino acids are not just building blocks, but a chemical alphabet, and the isotopic gradients are a map, a set of coordinates, or a schematic written not in symbols, but in the very atomic weights of the elements themselves. Is it conceivable that we are not looking at a natural wonder, but at an artifact, a message in a bottle cast into the cosmic ocean by an intelligence so ancient that its star has long since faded to ash? The implications of this tripartite mystery are as vast as they are perilous. If this is a capsule, even a natural one, the scientific opportunity is unprecedented. The dust particles escaping its feeble coma, captured by a carefully designed spacecraft mission, could provide a catalogue of molecular structures never seen on Earth. This would be a new chemical alphabet for synthetic biology, offering novel enzymes, novel metabolic pathways, and a profound understanding of the universal principles of life. It would be the ultimate gift from the cosmos, a recipe book from the dawn of time. But with such a gift comes an existential caution. If the contents are intentionally crafted, the requirement for planetary biosecurity protocols becomes not a precaution, but an absolute imperative. The standard quarantine procedures used for lunar samples or asteroid returns would be laughably inadequate. We would need to construct a laboratory of unprecedented isolation, perhaps in a high Earth orbit or at a Lagrange point, a facility where the capsule's material could be studied without any risk of contaminating Earth's biosphere. The very act of opening this billion-year-old freezer could unleash something we do not understand, a biology based on a different template, or something else entirely. Do we have the right, or the wisdom, to break a seal that has held for longer than our planet has existed? This single object, 3I Atlas, thus stands as a silent sphinx at our celestial gates, posing a riddle that challenges the very boundaries between natural history and cosmic archaeology. Its frozen heart may hold the answers to life's origins, or it may hold a message we are not yet equipped to understand. As we prepare our telescopes and design our missions, we must confront the fact that we are no longer merely observers of the cosmos, but potential interlocutors. What will we say, and what will we learn, when we finally reach out to touch this ancient traveller? And as we ponder the profound isolation of this frozen archive, our minds inevitably turn to the only other interstellar visitors we have known, each a unique and contrasting chapter in the same enigmatic story. How does the silent, dark mystery of 3I Atlas reflect against the bizarre, tumbling form of Oumuamua and the familiar, yet alien visage of Borisov? The cosmos has presented us with a trinity of enigmas, a collection of 3 interstellar visitors, each a unique keyhole through which we might glimpse the vast, uncharted territories beyond our solar system. The first, the perplexing one, Oumuamua, arrived as a silent, dark, and elongated traveller, a cosmic needle devoid of the characteristic coma and tail that mark a comet's journey. The second, 2I Borisov, was a familiar sight, a classic comet in exile, boasting a magnificent tail rich with water and dust, a fragment of a foreign star system behaving exactly as our models predicted. And the third, the ill-fated Atlas, offered a brief, tantalizing performance, activating early with the clear spectral signature of hydroxyl, yet displaying only a faint, almost reluctant tail, its light revealing an anomalous composition of metals before its premature disintegration near the Sunday. 3 guests, 3 distinct answers to the question of what exists in the dark between the stars, and yet, together, they pose a far greater question about the nature of the universe itself. According to current models of planetary formation, the sheer diversity of these objects is the first and most profound anomaly. The prevailing nebula hypothesis suggests that star systems form from a collapsing cloud of gas and dust, with planets and smaller bodies coalescing in a relatively orderly process. One would expect, therefore, that interstellar interlopers would be predominantly cometary, icy planetesimals flung from their nascent systems by gravitational perturbations. Borisov fits this narrative perfectly, a textbook example of a volatile-rich body. Yet, Oumuamua defied this expectation entirely. Its lack of outgassing, its peculiar shape, and its non-gravitational acceleration presented a puzzle that conventional astronomy struggled to solve. Scientists suggested this could be due to a unique evolutionary path, perhaps a body stripped of its volatiles by intense stellar radiation over eons, leaving behind a barren, rocky shard. But that does not account for the precise nature of its acceleration, which behaved less like the jetting of gases and more like a steady, gentle push. And what of Atlas, which seemed to possess volatiles yet failed to produce a significant tail, as if its ices were bound within a strange matrix or protected by an unorthodox surface layer? If these three objects are a representative sample, then the inventory of the galaxy is far richer and more complex than our simple models of cosmic detritus would allow. Are we witnessing not a simple statistical spread, but a fundamental classification of interstellar matter? This leads us to the first level of classification, a spectral and physical taxonomy. We can categorize these visitors not by their point of origin, which remains unknown, but by their intrinsic physical properties and the light they emit or reflect. Borisov represents one clear branch, the volatile-rich comet. Its spectrum was a vibrant tapestry of molecular lines, with cyanogen and diatomic carbon painting a picture of a primordial ice ball, a preserved relic from the outer reaches of its home system. Its physics were governed by the sublimation of ices, the gentle yet persistent rocketry that sculpted its magnificent tail. Oumuamua, in stark contrast, occupies a second, almost paradoxical branch, the inert, rocky asteroid. Its dark, reddened surface, its lack of detectable gas or dust, and its elongated form suggest a body shaped by processes we have yet to fully comprehend, perhaps through intense tidal forces or a unique collisional history. Its physics were dominated not by outgassing, but by its density and the subtle, photon-driven nudge that propelled it. Atlas, however, may represent a third hybrid branch, the volatile pore or masked comet. Its early detection of hydroxyl confirmed the presence of water ice, yet its faint tail and unusual metal signatures hinted at a body with a depleted surface layer or a crust rich in refractory materials, its volatile heart hidden beneath a deceptive shell. Could this tripartite division, the icy wanderer, the barren shard, and the cloaked enigma, be the fundamental archetypes of interstellar travel? Venturing beyond mere observation, we must consider the speculative hypotheses that these objects inspire. Could Oumuamua's anomalous acceleration and strange shape be evidence of a more exotic nature? One bold hypothesis posits it as a derelict light sail, a fragment of a vast, ancient solar sail from a civilization that has long since turned to dust, its machinery silent, adrift on the cosmic currents. Its flattened form would be ideal for capturing radiation pressure, and its tumbling motion the final, slow spin of a ship whose navigators are gone. Borisov, in this speculative framework, is the simple common iceberg, the workhorse of the galaxy, unremarkable in its composition, but a testament to the ubiquity of water and organic materials. It requires no extraordinary explanation. It is the baseline against which the strange is measured. And Atlas, with its premature activation and muted activity, suggests an even more intriguing possibility, that of a technological artifact, perhaps a probe equipped with a thermal engineering system. One could imagine a craft coated in a specialized material, designed to absorb stellar radiation with maximal efficiency. Its outgassing, not a natural process, but the controlled venting of coolant or the sublimation of a protective ablative layer, its spectral metals, the signature of its engineered hull. Are we, in our haste to find natural explanations, overlooking the faint signatures of cosmic engineering? This naturally leads to the second level of classification, a taxonomy of origin. Each of these objects must have formed in a specific environment within its protoplanetary nebula, a birthplace imprinted upon its composition. Borisov, with its abundant water and simple molecules, speaks of a cold, distant nursery, in the outer reaches of its star system, a region akin to our Kuiper belt or Oort cloud, where temperatures are low enough to preserve pristine ices for billions of years. Oumuamua, barren and dense, suggests a radically different cradle. Perhaps it was forged in the inner, hotter regions of a system, close to its star where volatiles are boiled away, leaving only rock and metal. Or, more dramatically, it could be a fragment of a planetesimal, torn apart by a tidal encounter with a white dwarf or a neutron star, a shard of a world rendered down to its core. Atlas, with its mixed signals, implies an intermediate or complex origin, a body that formed in the transitional region between the rocky and icy zones, or one that has been heavily processed, its surface baked and altered by a long-gone stellar companion, leaving it with a volatile interior but a refractory metallic crust. Do these three visitors map out the three primary developmental zones of all planetary systems? The fiery forge, the temperate gateway, and the frozen reservoir. The third and most profound level of classification moves beyond mere physics and origin into the realm of function and survival strategy. If we consider the interstellar medium not as an empty void, but as a challenging environment through which material must travel, then each object may represent a different evolutionary solution to the problem of cosmic voyage. Borisov employs the strategy of mass and redundancy. It is a massive iceberg, its volatile reserves acting as both a shield and a propulsion system, allowing it to weather the journey and announce its presence spectacularly when it finally approaches a star. It is the hardy, long-range voyager built to last. Oumuamua, conversely, may represent the strategy of stealth and minimalism. Its dark, non-outgassing surface allows it to slip through planetary systems largely undetected, conserving its integrity. In a speculative light, if it were an artifact, its silence and lack of coma could be a design feature for long-term, low-maintenance travel. Atlas, then, might embody the strategy of active thermal management. Its early controlled release of volatiles and its unusual composition suggest a system for managing stellar heat, perhaps to prevent catastrophic fragmentation or to enable a specific maneuver. Its failure could be seen not as a natural death, but as a system overload, a calculated risk that did not pay off. Are we looking at three different philosophies of interstellar existence? The robust survivor, the stealthy wanderer, and the high-strung engineer. The implications of this trinity are already reshaping the future of astronomy. This trio has become the essential training set, the standard candles for a new generation of discovery algorithms being developed for the Vera C. Rubin Observatory and its legacy survey of space and time. By teaching our machines to recognize the spectral fingerprints and orbital peculiarities of an Oumuamua, a Borisov, and an Atlas, we prepare them to rapidly identify and classify the dozens, perhaps hundreds, of future interstellar visitors that LSST is expected to find. This classification is not an academic exercise. It is the first and most critical step in target selection for the next great endeavor, interception missions. When the next anomalous object is detected on its inbound trajectory, the decision on whether to dispatch a rapid response probe will hinge on our ability to quickly assess its type. Is it a volatile-rich Borisov, promising a trove of pristine foreign astrochemical data? Is it an inert Oumuamua, requiring a close-pass mission to image its mysterious shape? Or is it a strange hybrid like Atlas, demanding immediate spectroscopic analysis to decode its anomalous activity? These three visitors have given us the Rosetta Stone for deciphering the language of interstellar objects, but have we yet learned to read between the lines? As we train our telescopes and algorithms on the dark, preparing for the next visitor, one cannot help but wonder about the fate of those we have already lost to the inner solar system. The story of Atlas, in particular, remains tragically incomplete, its final act played out too close to the sun for our instruments to observe in detail. But what if we were given a second chance? What if we could witness, with unwavering clarity, the ultimate trial by fire?